right, good afternoon. Looks like we're running behind, so they told me I couldn't talk much and we have to get done. So with that, let's go ahead and get started with the micro-apps paper that I'm covering today. Fixtures are a problem for most of the industry. Whether you're in the digital world or the RF world, removing fixtures is the challenge. Historically, there have been two methods used to remove fixtures. One is you can use EM simulation or other simulation technology, come up with a model for your fixture. Once you have the S2P file or the S4P file for your fixture, then you use standard de-embedding techniques and remove that fixture. Now you're relying, though, on the accuracy of the material properties and other things for that model. Probably the most common method that's been out for a long time is using a TRL calibration, a through reflect and one or more lines. I've worked with customers over the last 10 years and probably helped people build 30 or 40 TRL cal kits, and that was the way that we always recommended to get the fastest way to get accurately remove your fixtures. Some of the assumptions quickly on TRL. First, you need a through, which is the left fixture and the right fixture put together. Then you may need one or more lines to cover the frequency range that you're doing, reflect of some kind, either an open or a short, and then ultimately you have a DUT that you're going to measure. There are some assumptions, and most people don't pay attention to those, but basically all the connectors and launchers are supposed to be identical. All the lines have the same transmission characteristics. They only differ in length. You use the lines to a maximum of 20 to 160 degrees, which is why you need more than one line. And if you're doing any differential fixturing, coupling is not removed. So the example I'm showing here of a differential kind of device, any coupling in this fixture is not removed. That's the way life is. A few years ago, we came up with another TRL calibration technique, which is a 4-port TRL. It looks very similar. You have a through, multiple lines, a reflect of some kind. Same constraints, assuming the lines are the same, connector repeatability and so on. The additional assumptions are that the mode conversion is less than 30 dB and the skew between the lines is less than 10 degrees. And in this case, you'll get the fixture removed, which includes coupling. So if you have coupling in this area, it will remove that. So we have some people that started to do differential in the signal integrity world, differential TRL. Well, about that time, we came up with some new technology, which we called automatic fixture removal. This first came out in the market about 5-6 years ago. And the original assumption was you put the two fixtures together, the right and left half, and to make a through structure. That's the same as a through in the TRL cal kit. The original assumption was the left and right sides had to be symmetric. Over the years, we've been able to prove the algorithm, so they no longer have to be symmetric. They can differ in length and match. And the differential version is the same. It had to be symmetric right to left, which we've removed. So the only thing that's left now is symmetry top to bottom and no mode conversion. These techniques work very well. Customers in the signal and the digital world have been using them for quite a while. And comparisons of this technique to TRL have shown that you get comparable results with one standard versus that larger number of standards that I showed previously. So most of the customers are moving towards this 2x through. So I think the industry is accepting that as an equivalent to TRL, especially when you're on planar materials like PC boards and things like that. If you're still in the coaxial world where everything is well controlled with air dielectrics, you don't need to deal with these things. So the new version of this, which we came out in DesignCon in February and we're applying to the RF world, is a 1-port version. So people were asking, well, gee, instead of building a fixture, can I just measure my fixture before I load the part? And so we worked on the math, and we now have what we call a 1-port AFR, and you can either have a single-ended or differential. It can either be an open circuit or a short. One of the things to be aware of is radiation. Most of the planar materials, that's not a problem. If you're doing things in coax and have center pins at higher frequencies, you can radiate, in which case you want to use a short instead of an open circuit. But these are the easiest to fabricate, the smallest footprints. For probes, especially GSG probes where you might have coupling in there, some good ways to do that. If you're making packages, you can measure an open fixture, load the part in, and you're good to go. Same thing on PC boards. So this is a very quick way, and we actually have it set up there if you want to take a look at that, and as to measure your fixtures. Now you may say, how in the world can you get a two-port S parameter model from just an S11 measurement? Okay, sounds like magic, right? All you're measuring is S11. So how can I really model that whole fixture? Well, I do have some data to show you. I do this paper about 6 months ago, so I have more data more recently. But if we look at this, this was a board that we built for the original AFR where we did the 2x through. Built on Rogers material. We chose something that was low loss. We offset the lines to minimize the weave variations. We did not back drill the vias purposefully. We wanted to leave a little bit more of a challenge to see how well this worked. Our device under test was a mismatched line. And with this, we had a TRL cal kit on here. We had both a single-ended TRL cal kit and a differential cal kit. So we're able to do comparisons to show how accurate AFR was to TRL. This was, again, the original 2x through method. And this was about 5 years ago. So I went back to use the same board again. And I'm using it with the one port. So I just used the reflection on there. And if I look at the models, the fixture models that I generate, based on the through or based on the open, the difference of impedance is about 1/4 of an ohm, and the length difference is about 1 picosecond. So we're generating very good correlation between the two, but really the answer is, okay, that looks nice, but what happens if I really try to use these fixtures and measure a device under test? Before I get to there, on the device under test, I told you I had those big vias in there, and that might have caused some concern. Turns out there is limitation for if you're doing TRL or AFR, and one of the sort of good rules of thumb is you plot the insertion loss and you plot the return loss. And at the highest frequency of interest, if these don't cross, you're generally in good shape. If you have a really poor match or really high loss, then you start to get into problems with that. But so in this case, we're still okay out to 20. Things look pretty good. So I would assume I would get some pretty good results. Okay? Doing on time here. So I generated 2 fixture models. This is an S2P file based on cutting a through in half or simply measuring a, I think this was an open at the time, and generating the fixture. So you see the 2 fixtures are very, very similar, the blue and the red. The blue is from the through and the red is from the open. Very small differences, but again, very good correlation between the two. So that's the fixture model. Okay, that's an S2P file of that fixture. So now if we de-embed that fixture from the device under test, how well does that work? Okay, try again. There we go. So what I'm showing here is the Beatty standard. This is that big via that we did not back drill the vias. The green here is the device with the fixture. Here's the Beatty standard. We're changing the impedance and coming back up and so on. So there's my fixtured measurement. Okay. And then I did 3 ways to remove the fixture. I used a TRL calibration where I used line through, multiple lines, and a reflect. I just used the 2x through, mathematically cut it in half and de-embedded it. And then I used the open fixture, created a model based on that, and removed it. So if you look closely, we're moving from the green, which is the fixture measurement, back to this group of measurements over here. And again, very good correlation between the measured, between TRL through and open circuit. I think I have a blow up of this coming, yeah. One of the differences is if you look closely, once you get past the device, the final DC value, there's a little bit of variation in that depending on your method. Basically, we have to compute DC. We don't measure DC directly, and so when you put on a short or an open or the through, the algorithm isn't absolutely perfect, but in reality, you don't see that effect really in your devices at all when you make that measurement. So if I zoom in on the bottom a little bit here, if I use my TRL calibration as my reference, then how different is the through and how different is the open? So if the TRL is my reference, this is 0.2 of a dB per division for this area down here. You see the through is about 1/10 of an ohm off, and the open is about 1/4 of an ohm off. Well, is that good or not good? Some people might say, I want that measurement to be to 0.01 ohms. Okay, well, they better pay a whole lot of money because if you think you can get 0.01 ohms, that's tough. So let me put that in perspective for you. The TRL has multiple lines. Okay, These were built on Rogers 4350 material, very good material. Okay, but even building on good material, you get some variations on the line impedances. Depends on how they're etched, how the board is fabricated. And if you look at the variation of these lines, you will see about a half of an ohm variation in those lines. Okay, so if line 1 versus line 2 versus line 3, I can get about a half of an ohm variation, which is pretty typical. Then that 0.1 and 0.25 definitely falls within the range of the line variations that we're seeing. So overall, I think you'll agree that those are pretty decent results. All right, so let me switch to one. Let's look at that in the frequency domain. Here I'm overlaying the through measurement, which agrees very well with TRL. I just made the slide a little bit simpler here with less plots. Looking at S11, well, actually all 4 S parameters. And what you'll notice is that the last half to full division of the measurement, we're starting to see some variation in here. Especially on the one port. The one port, there's some issues with gating and filtering and windowing and other things. We're still working on that so that you can get a little bit of variation at the very end. And you see I plot the difference here between S21, the two methods. So we're about 1/4 of a dB except for the very end. So if you can measure a little bit wider than you need, you're in good shape. I think there's ways to work on that. We're still working on that. But customers have found this to be very valuable and accurate as is. One more case study. This time I'm going to use some simulated data. I'm going to basically create my own fixture. I'm going to use about 2 inches of FR4 lossy material, and I'm going to build a Beatty standard in the middle, put some capacitors in to represent my a via or a connector launch. And so basically you see the fixtured measurement here is in blue, and then the actual dud itself is in red. So I'm going to start with the blue and hopefully get back to the red. So basically I'm going to simulate a through. I'm going to simulate an open, and I'm going to simulate a short. Those are what I'm going to use for my measurements, okay? So I can control exactly what those measurements are. I'm also going to simulate the fixture in 50 ohms. That's my target. So if I take and cut the through in half, or if I take that one port measurement and try to generate a model, I can compare it to what theoretically should be the right answer, right? That's my simulated result. I'll also simulate the device under test in 50 ohms and can use that to compare my results. So with that, let's take a look and see what we have. In the top left, I'm plotting T11 or a TDR plot of the blue trace is a simulated, so that theoretically is the right answer because that's what I'm trying to get to. Then I do a through, I cut the through in half and generate a fixture model. I use an open circuited fixture and generate a model, a short circuited, generate a model, and then a combination of the open and the short. You see the green and the yellow is a little bit of beading in here, a very small amount, and you see they're out of phase. So if you're able to use both the short and open, it actually gets a little bit better. But if you look at that, again, the results are very, very good. S21 basically looks quite well. If I zoom in on S11, the only really differences you see are at the low end here. Of course, I'm 50 to 60 dB down. And a difference in 50 or 60 dB down, you're not going to see it all in your measurements. I don't think too many people are trying to get down there, at least in the planar world. But again, you see this issue at the high end, a little bit of artifacts happening at the high end, okay? But again, excellent agreement between all those 3 models with the simulated results. And so we look at that Beatty standard again. The purple color is the measurement with the fixture. And then the other traces that all lay on top of each other are the different measurements. The simulated result based on the through, based on the open, based on the short, and the combination. So we're basically going to correct from the purple to these traces up here. Or in the case of S21, this is with our fixture, and we're going to bring the data up to here. That's really our device under test. So if I zoom in on the reflection, S11, if I just look at this last couple divisions, we'll see again, I have the simulated result in blue, the through in red, open is green, and short is yellow. Again, very good results. So through does the best job, and the open and short, again, you see in that last division, have a little bit of variation in there, something I think where we can improve the algorithm over time. Same thing if I zoom in on S21, excellent results until I get at the very high end. And with that, similar results on the TDR, the Beatty standard. 0.15 ohm and 0.03 ohms, and comparing those, very good results. And so in conclusion, hopefully I've shown you that this is an interesting technique. Since I wrote this paper originally, I've done more and more measurements. Where now I say it seems to be effective. The more measurements I make now, it really seems to be a very good way to do that. So with that, I would like to wrap up and say thank you.